All right, so let's go ahead and get started. Before we discuss and get into our topic today, I know that last time the problem that we did was a fairly large problem and large in scale, but in the end, I'm sure that you might have a question or two on some of the details, but I'm just wanting to make sure that you all understood the general process behind what we did last time. Is everybody okay with that? Okay. Now, what I said last time, which might have, sort of gotten lost in all the murky details that we talked about, is if you recall and really think about everything that we've done this entire semester, everything that we've done so far has all been focused around the same problem, and that is that force equals stiffness times displacement. And that's everything that we've done all semester in some fashion or another. Well, we're actually done with that, and I want to move on to other types of problems in finite element analysis. And the other, I guess, main class of problems that you deal with in the world of finite element analysis are eigenvalue problems. In other words, an eigenvalue problem is something like a vibration problem or a buckling problem, and things like that. Eigenvalues also have other applications in things like stress analysis and whatnot, and I want you all to kind of have a general idea behind what it is that these software programs are doing when they report stresses to you and values and what have you. But I also am probably, it's probably not a horrible prediction to say. Let me just ask, how many of you have heard of an eigenvalue? Okay, so some of you might have, but that's fine. If you haven't taken a direct course in linear algebra, you probably haven't heard of an eigenvalue, and that's fine. So what I'm going to do is actually start off by just explaining what an eigenvalue is, and then we'll see a simple example, but a very powerful example of where we will use eigenvalues for things like stress analysis and finite elements and what we do. So let me start off. Let me get some of these handouts passed out. So 1, 2, 3. There's that. There's that. There's that. There's that. And there's that. Okay, so let's start off and actually kind of talk about eigenvalues and what they are. So an eigenvalue is a sort of a unique type of problem in linear algebra, and it's kind of odd the first time that you see it, but when you take some time and actually digest it and sort of get an understanding behind how the process works, it's actually pretty neat. So eigenvalues are kind of like special terms that are related to a given matrix. To think of an analogy, you all, given, let's say, a square matrix, know generally how to compute a determinant. A determinant is a very characteristic value of a given matrix, and a determinant tells you quite a bit. For instance, if your determinant equals 0, you know that a matrix does not have an inverse, right? That's one of the things that determinants tell you. And they have a number of other applicable points about them. Eigenvalues are also, a set of characteristic constants about a given matrix. Now, eigenvalues are the number of eigenvalues associated with the matrix is a function of its size. For instance, if you've got a 2 by 2 matrix, that matrix will have at least, will have 2 eigenvalues. If it's a 7 by 7 matrix, it'll have 7 eigenvalues. Now, what is an eigenvalue? Okay, let's go back to the concept of matrix multiplication. Okay, so if I take a matrix times a vector, I will get a vector, right? Like if I have a 5 by 5, a square 5 by 5 matrix, and then a 5 by 1 column vector, the resulting answer will be a 5 by 1 column vector, right? That's what matrix multiplication does. But what if I propose to you that instead of doing all that matrix multiplication, that I propose to you that there's a special number, that if I took that vector and just multiplied it by that number, I'd get the same answer. Okay? That's an eigenvalue. An eigenvalue is a characteristic value associated with a matrix such that you take that matrix and multiply it by a given vector, you get the same thing as if you just multiplied that eigenvalue by that vector. Now, one thing I will say, it's not just any vector, okay? We have eigenvalues, and with each eigenvalue, we have an associated eigenvector, okay? So we'll explore how you determine that today. It's not terribly difficult. In terms of derivation and actually getting to the problem, it's actually pretty simple. So I propose to you that there is some magical value lambda, some magical constant that we call an eigenvalue, such that a matrix times this vector equals lambda times this vector. So if I subtract, I say, all right, AV minus lambda V, that has to equal 0. Just subtract on both sides. Okay? Now, if I want to factor out a common term, I can do that. One thing to keep in mind is you can't just simply pull the V out and just say A minus lambda in parentheses times V. You have to have an identity matrix in there for your dimensions to make sense. Again, we're talking about matrix math, not just 2x plus 3y or something like that. So you have to make sure that you're maintaining your appropriate dimensions here. Now, this lends itself into a particular problem in the world of math, the susceptibility in a given problem to yield trivial solutions. And it can be shown, again, one thing I will say, this is not a linear algebra class. I'm not in the business of teaching you all linear algebra. You all can take that if you're interested. But it can be shown that for an expression like this, the only time you're going to get a non-trivial solution is when the determinant of this matrix equals 0. And what'll happen is this. When you take the determinant of that matrix, you'll have a polynomial that results in the end. And that polynomial, if it's a 2 by 2 matrix, it'll be a polynomial to the squared term, like lambda squared minus 3 lambda plus 4 equals 0. There's two possible answers. If it's a 3 by 3, it'll be a cubic equation, and so on and so forth. And that's how you'll solve for your eigenvalues. It's really about that straightforward. Okay? Now, real quick, just so we're all clear, does everybody remember the concept of how to compute a determinant? For instance, if we're dealing with a 2 by 2, it's just AD minus BC. If you're dealing with a 3 by 3, y'all probably remember this when you did statics. It's called the rule of Saris. You take these two columns, stack them over to the right, and say all the terms going like this equals all the terms going like, or all the terms going like this, sum them up, minus all the terms going like that, not equals. You all have done that before, right? Okay. Now, one thing, if you're dealing with 4 by 4s, 5 by 5s, 6 by 6s, eigenvalue algorithms, or determinant algorithms get pretty complicated or pretty large. It's all about taking all of the associated permutations and multiplying them together. Even permutations are positive, odd permutations are negative, and summing them up. So determinants can get pretty nasty when the matrices get bigger. Luckily, there's a function in Excel to calculate determinants. It's just mdeterm of whatever array you're looking at. You don't have to do the Control-Shift-Enter function. You can if you want. It won't give you a different answer because determinants are a number. They're not a matrix. So you don't have to do the Control-Shift-Enter. All right. So let me show you how we compute eigenvalues for a given matrix because it's pretty simple. All right. So let's say we've got this matrix, 1, 1, minus 2, and 4. This matrix, the reason why this matrix was chosen is because the eigenvalues come out to be nice, even integer numbers. There's no decimals all over the place. Okay, so here's my matrix. What I'm going to do is I'm going to subtract lambda times I. So here's the matrix. I say, all right, let's subtract lambda times I. So here's lambda. And I is just the identity matrix. 1's along the main diagonal, 0's everywhere else. Sound good? Okay, so subtract these out. And remember, when you do matrix subtraction, you just individually, term by term, subtract everything. And what you find is, what is the difference between this matrix and this A minus lambda I? Well, along the main diagonal, it's just like 1 minus lambda, 4 minus lambda. Every other term is exactly the same. Okay? Make sense? Now, how do we take the determinant? Well, it's a 2 by 2, right? So we say this times this minus this times this. Make sense? Okay, so the A times D term is this, this term times that. Remember that whole foiling thing that you learned back in middle school or what have you? So front times front, outside times outside, inside times inside, last times last. You all done that, I'm sure. Minus this here. So minus a negative, that's how we get that positive term there. Collect everything that's common terms and see how we get a quadratic, a polynomial to the second order. Lambda squared minus 5 lambda plus 6. So again, I said a 2 by 2, you'll get a polynomial that its highest term is lambda squared. If it's a 3 by 3, you'll get a cubic polynomial, and so on and so forth. So here's this polynomial. I've got to believe that you all can do this, you know, on your own, right? You should be able to solve that polynomial, quadratic formula, whatever you want, and what have you. Is everybody good with this? Okay. Now, a couple of things I do want to show you, just so that you all can do this in Excel and you all have the ability to do this on your own. How many of you have ever used goal seek in Excel? Have you ever heard that term, goal seek? Okay, all right. Goal seek is a very simple but very powerful tool in Excel beyond finite elements. If you've got some really complex equation and you're trying to figure out an associated value, and you don't want to like do all the nasty mathematics associated with it, you can have Excel just pick a number, and then what you do is you use this command called goal seek, and Excel will iterate the value of that number such that you achieve your solution. So I'll show you how this works. All right. Okay. All right. So here's my Excel sheet. Okay. All right. And let me put in my original matrix. And what was it? It was 1, 1, and it was minus 2, and it was 4. Okay. Now the way goal seek works is you have to start out by making an initial guess. Just guess a random number. Okay. So I'll say that for my first eigenvalue, I'll put an eigenvalue right here. Eigenvalue, it's close enough. I'll just guess 5. It doesn't really matter. You can just guess whatever you want. Okay. And let me highlight that number because I want that number to be of interest. Okay. Now, everything that you do from here on out, you need to reference that cell, or don't, just type in the number 5, say equals, and then refer to cell, what is it, F2, okay? Because everything that you do from here on out has to be based upon what's in that cell, because it's going to iterate that value to change everything else. So this is my A matrix, right? And then I've got, what is it, what's the lambda? Lambda times I is just going to be what? Equals 5 and equals 5 and then 0 and 0, right? So that's lambda I, okay? And then we'll say, okay, what's the difference of those two? So just term by term equals that minus that. And then ultimately what I need to do is find the determinant of that, right? Yes, I rep that, yeah. See, it equals F2, yes, exactly. And then equals m determ of that. Oh, didn't put my parentheses there, so it didn't find it. Oh, come on. There we go. Now you can do the Control-Shift-Enter if you want. It doesn't matter. It's just a number. So based on a value of 5, I get a determinant of 6. So what happens if I make that eigenvalue like 56? Okay, see how the determinant changes, right? So what I'll do is this. If you look into Excel and you look in the tabs on the top, you'll see a Data tab. Click that, and there's a number of tools that you can use to do data analysis, sorting data, and what have you. And then over here, there's a button or a drop-down menu that says What If Analysis. And here you'll find your goal seek. There is another solver analysis tool that you can add on to Excel, and it actually is much more powerful. It'll do more. But if you're trying to do something really simple, just go with GoalSeek. I think it's a little more straightforward. Okay, so GoalSeek, okay? So when you, and I apologize for you all watching in the class because it's Excel's native font. It's pretty small. But if you look, what you'll see is set cell whatever to a given value by changing something else. Now we're doing an eigenvalue problem, so what we want is this determinant where it says 2862. We want that to equal 0, right? So what I'll do is I'll say set cell, and then you can click this little button right here. I want to set that equal to 0, and I want it to be 0 by changing what? The eigenvalue. So I go here and I hit by changing that, hit OK, and it's iterating, and it's funny how it gives you an answer. Now, because Excel is using a numerical iterative approach, this happens, okay? Instead of it being 3, even though the answer is exactly 3, you'll get 3.00000, whatever. That's fine, okay? Especially for our purposes. I mean, we're talking about approximate analysis techniques and what have you. Now, I know that I'm sure that there are some of you who are going to see this and go, no, not this, not Matlab. Matlab, oh goodness. This is not bad. I will say that I don't, for this class, I prefer using Excel just because I think the visual assembly process and understanding that process and being able to apply your stiffness terms appropriately, I think that's more powerful. That being said, things like Matlab are much more powerful for doing eigenvalues. It's the one thing that I think is a little tough to do in Excel. Eigenvalues are actually pretty powerful to compute in Matlab. Let me see if I can make the font a little bigger. Let me see. Preferences. Fonts. Let's see. Maybe I can make that, I don't know, 18. Y'all read that? Is that a little better? Okay. So what you can do, and I mean this is about as simple as it gets. You can say A equals, and then you use brackets to define a matrix, use commas to define in between individual rows, and semicolons to define or split rows apart. So 1 and 1, and then semicolon, what was it, -2 and 4? Is that it? All right, so you just hit enter, and now it actually defines the matrix. It even draws it out for you. And then all you have to do is do eigenvalue of A, and bam. It's actually pretty powerful. And you're going to see that here in a little bit, how eigenvalues can take a little bit longer with Excel. So it's just something I figured I'd mention. So, and if you all don't have access to Matlab, you can, or like on your personal computers, there's I will go ahead and mention this. This is probably more for the mechanical folks that might have to use it for their research, but there is a program called GNU Octave. And this is just worth mentioning. GNU Octave is, I mean, it's pretty much just like Matlab, and it's free. It's open source. So if you're interested in doing that type of data analysis and you need Matlab type software but you don't have it on your personal computer, this will run .m files and it should be fine. So just a piece of information. So I mean for my research I use Matlab files to generate finite element meshes, and I can do it in here just as well as I can do it in Matlab. So just something worth mentioning. Okay. All right. All right. Does this make sense so far? Okay. Now, eigenvalues do not complete the entire picture. There's also associated eigenvectors. Okay. We're going to find kind of an interesting result. I'm just going to tell you right off the bat. When you determine eigenvectors, you actually get an infinite number of associated eigenvectors, but they all follow a given pattern. And I'll show you how this works. Now, how we do that, we basically just plug and chug and see what we get. Now, our eigenvalues for this problem were 3 and 2, right? Everybody okay with that? All right, so let's start off with the first one, 3. Okay, so here's our problem. A times V equals lambda times V. Now, we don't know what the vector is. That's the whole point. We're trying to determine what V is in this problem. Okay, so, excuse me. So A times V equals 3 times V, right? Distribute on the right, it's just 3 times x1, 3 times x2. Everybody okay? Now, what about matrix multiplication on the left? Well, it's 1 times x1, 1 times x2, and that's how we get this. On the bottom, negative 2 times x1, 4 times x2. Sum them up. That's what we get. Everybody okay with that? Okay. So going back to, now we have 2 equations and 2 unknowns. Now, what I'm going to do is this, and this is where things get a little interesting. Okay? Let's look at this group here, and I want to see how I go from this upper group to this down here. Okay? Now, let's look at the top equation. I want to bring everything to the left, so I need to subtract 3x1 from both sides, right? So if I subtract, I have x1, and I take away 3, I have negative 2, right? So see how I went from here to here? Now let's take the lower equation. I have 3x2, bring that over. So 4, take away 3, and I have this. I got the same answer, the same equation, okay? And that can happen, okay, with eigenvalues. What that means is when you have 2 equations and 2 unknowns, but the equations aren't independent of one another, you can have an infinite number of answers. Now, if I just take any one of these and simplify it, I get an answer like this. So what this is basically saying is that whatever x2 is, it's double of whatever the first one is. So I propose to you that our eigenvector will be something like this, like r and 2r, okay? Now, if you don't believe me that that works, let's check this out, okay? Let's take this one, okay? So we'll say that this one's 1, so the bottom value has to be 2 because we got r and 2r. So if I wanted to make it more complicated, I could say, okay, well, how about 7 and 14, or 6 and 12, or 10 and 20, or 48 and 96, whatever, it doesn't matter, okay? Everybody with me? Let's carry this out. AV equals lambda V. Let's look at the right side. Lambda times V. Here's lambda, V is 1 and 2, multiply it out, we get 3 and 6. Make sense? On the left, here's A and here's V. Multiply it out. 1 times 1 plus 1 times 2. Negative 2 times 1 plus 4 times 2. Carry it out, you get 3 and 6. It's the same answer, okay? Again, the purpose of an eigenvalue is to come up with that magical number such that I can multiply a whole matrix times a vector or that number times the vector and I get the same answer. That's what an eigenvalue is. The same thing works if you do a problem incorporating something like 7 and 14. Do the numbers get bigger? Yeah, but you get the same result. I mean, if you look at the matrix multiplication, 1 times 7 and 1 times 14, that's 21. 3 times 7, that's 21. Make sense? All right. And we can do the same process with the other one as well. Normally for what we do in stress analysis, because we like numbers and we like values, we usually report eigenvectors with the first value equaling 1. So whatever 1 is, we keep that down. Right. Does that make sense? Everybody good? Okay. So this is kind of like the same thing that you did in statics. We also like to report this in terms of a unit normal. All right, so let's go back to statics. How do you get a unit normal vector? Okay. Well, the first thing you have to do is you have to determine the length of this vector. How long is this vector? Well, it's the square root of 1 squared plus 2 squared, which is the square root of 5, right? So basically we're saying this vector has a length of square root of 5. If I want a length of 1, I need to divide the whole thing by that, and that's how we get this. Okay? It doesn't matter, again, what those values are. That is still an eigenvector, right? Because whatever this value is, this one needs to be double that. Make sense? Okay. Now, we can do the same thing across the board for the second one, and we end up getting that these two values are equal for lambda equals 2. You all can do that on your own if you want. Make sense? Everybody good? All right. Now, we actually find kind of a nifty little result, and I think this is just worth sort of showing so that you kind of see what's going on. This is our N matrix, and I call this, it's a lot like a rotation matrix. It's very, very similar to a rotation matrix when we apply an eigenvalue approach to stress analysis. The reason why is think about it like this. How many of you remember that whole thing called Moore's circle? Remember, you've given a stress state, you are trying to determine principal stresses, okay? In other words, I'm given a stress state, but that stress state is based on a coordinate system that I just made up. I just said, okay, we'll say this is my y-axis and this is my x-axis. But really, instead of this being the coordinate system, maybe this one's the coordinate system. Maybe that's what I need to look at. So what's the difference? It's all about your angle of rotation. Now, you all know by now we can do rotation with matrices. We developed rotation matrices, those beta matrices. Remember we did that for trusses? This, I propose, is basically the same thing. It is a rotation matrix. Watch this. Watch what happens when we do this. So, let me show you something. Okay, so here's our A matrix, right? Let me put that about right there. That's our A matrix, right? Our N matrix, what is it? It's equals 1 over the square root of 5, 2 over the square root of 5, and it's what? What is it, 1 over the square root of 2? Y'all have it? Is that right? It's like that, right? Watch what happens when we do this operation. We take N inverse times A times N. A lot like beta transpose K beta, right? Watch what happens. All right, so let's see if y'all remember how to do this. It might have been a while, but we say, all right, equals the matrix multiplication of the first two, which is the inverse of that one and that one. Then we have to multiply that whole thing. So times N. Control Shift Enter. And look what we get. We get a matrix that's filled with zeros everywhere else except the main diagonal. And what are the values along the main diagonal? 3 and 2. Those are our eigenvalues. Pretty nifty, right? Make sense? Okay. Now, I got ahead of myself because this slide says, let's use Excel to determine eigenvalues. Well, we kind of already did that. I got ahead of myself. Okay, anybody have any questions? Now, don't get me wrong, I like math. I wouldn't have gone into engineering if I didn't, but I like math that has a reason. In other words, I like to see its applicability, okay? And eigenvalues have a significant application in our world, not just in finite elements, but just in general stress analysis. This is interesting, or this should be interesting to anybody that is a civil engineer or mechanical engineer. There's an application. One of the nice things about eigenvalues, especially when it comes to something like a stress analysis problem, is eigenvalues, you can apply the same procedure for 2D stress and 3D stress, and it works across the board. You could theoretically do it for 1D stress, but it stops becoming stress analysis at that point because there's just one stress and that's it. But the nice thing is that you can apply this process across the board. See, in 2 dimensions, we had this nifty little trick called Moore's circle. And all we would have to do is just, draw our Moore's circle, and we would know what our maximum shear stress is, and we would know what sigma 1 and sigma 2 are, our principal stresses, okay? Well, I propose to you that what we're going to find is that sigma 1 and sigma 2, those are our eigenvalues. And our eigenvectors are basically going to illustrate to us our rotation, okay? Let me give you kind of an idea. So let's consider the following stress state. For the units, they really don't matter, but I threw them in there. We'll say they're in PSI. So 12,300 psi in the x direction, 12,000 or negative 4,200 in the y direction, and negative 4,700 for shear. So remember, positive stresses, remember those correspond to stresses in tension, right? We say that because tensile stresses tend to elongate, make the member get longer, increase in length. Negative stresses tend to decrease your length. So sigma x is positive, sigma y is negative, tau xy is negative 4,700, and that's our stress state. You all have done stuff like this before, I promise, okay? Now, I propose to you we can write these stress values in matrix notation. If you ever hear me refer to the term stress tensor, that's what I'm talking about. It's just stresses written in a matrix format, okay? So I propose to you this is our stress tensor, okay? Now what happens is when we're dealing with a two-dimensional stress state, what's going to happen is we have two different ways that we can determine principal stresses. We're going to get the same answer. The first approach is just to use what you learned in mechanics of materials or strength of materials, mechanics of deformable bodies, whatever you all called the class when you took it. And that's Moore's circle. And you all this should at least be vaguely familiar to the people in this room. I mean, just open up your mechanics book. I guarantee you it's there. So your principal stresses, sigma 1 and sigma 2, are, the average stress plus or minus this term that you see here, which is essentially plus or minus the radius of your Moore circle. So if I say, all right, let's just plug and chug, all right? So here's my stresses. So the average plus or minus the radius, plug and chug, do all the math, and I get sigma 1 is this and sigma 2 is that. So in other words, on my Moore circle, sigma 1 is about, 13,544 psi. Sigma 2 is negative 5444. So sigma 2 is over here, sigma 1 is over there. Make sense? Now, I also propose to you that there's another way we can do this problem. We can do it using an eigenvalue approach. So 12,300, negative 4,700, negative 4,700, negative 4,200. Use an eigenvalue approach. Take the determinant, and I know that equation looks a little messy. In practical applications, we wouldn't do that. We would just do it in Excel. Okay? Or we can do it in Matlab, however you want to do it. For the demonstration, it's probably quicker to do it in Matlab. What do we have? We have 12,300, 47, 47, 42. So there's our stress tensor, right? And then here's our stresses. And it's basically saying these values times 10,000. So take that, stretch it out a little bit, and there you go. Or if you want, you can look at it here. Either way you want. Oh, what did I do? Whoops. We have gotten through a lot of slides in this class. Okay. Does this make sense? Does everybody good? Anybody have any questions? Okay. All right. The nice thing about this is that if you use the exact same approach in 3 dimensions, it works just as well, and it actually works pretty nicely. So, all right, if you're doing 3 dimensions, you're going to have 6 stresses. We write that in a 3x3 stress tensor, as you see up here. A couple things to note. Remember, we have 6 total stresses in 3D, right? We have 3 normal stresses, 3 shear stresses. And if you look, that's what we've got here. So like if you see tau xy here, you see tau xy there as well. So there's only 6 independent terms that go in the matrix. And because of that, if you start going through it, you'll see it's symmetric. Okay? Make sense? All right. So we go through the same process that we use for an eigenvalue problem. We say, all right, let's take these stresses, this stress tensor, and let's determine the determinant of this matrix those unknown lambda values will yield, lo and behold, our principal stresses. Now, you all have, 3 by 3, if you use the rule of Saris and multiplied this out and had a big whiteboard and did all the algebra, you can actually simplify this out a little bit. If you take this determinant and do all the math and expand everything out, you can actually generate a polynomial expression that looks like this. And there are these terms, I1, I2, and I3. They are known as stress invariants, okay? And they're basically just a way for you to simplify that, that cubic equation. Because remember, what are we going to do? We're going to take these two columns, we're going to put it over here, right? Then we're going to say, 1, 2, 3, sum them up, 1, 2, 3, sum them up, and take the difference. That's a lot of algebra, right? I know you all love algebra, but that would be a lot of algebra, right? So I propose to you that there's a simpler way that we can compute those stress invariants, and it's like so. We have I1, I2, and I3. Okay? Make sense? We're going to look at doing this here in a little bit. Okay? Okay. So one nice thing, and one thing that's kind of interesting, and you can actually prove this, which, again, it's just a function of algebra, but if you've got a three-dimensional stress state, you're going to have at most 3 principal stresses, a sigma 1, a sigma 2, a sigma 3. Okay? These stress invariants, you can actually also recalculate them and get the same answer. Like, for instance, take I3. To calculate I3, you would take the determinant of this. Okay? I also propose that to calculate I3, once you get your principal stresses, you can just say 1 times 2 times 3, and you'll get the same answer. It's actually pretty nifty. For sigma, or for I1, you can add up the terms along your main diagonal or add up your principal stresses, you get the same answer. So it's kind of nice because it's a check to see whether or not what you're doing is correct. Okay? Sound good? Because we're going to do a problem here in a little bit. We'll do it together. Now, one final thing I'll point out is you can look at the data that's been put out there. You can look at experiments that have been done on this, and you find that most materials really don't behave much differently based on their level of hydrostatic stress. In other words, how many of you have ever heard of the Marianas Trench, the deepest point in the ocean on the planet? Okay? If I were to take a block of steel and test it here versus testing it down at the bottom of the Marianas Trench, I wouldn't get any difference in its properties, because material properties are really independent of hydrostatic stress. If anybody, and there's a number of applications that you've probably already done this in some fashion or another in some of your classes. And I'm sorry that I relate everything to civil engineering because it's what I know. But for you geotechs out there, you've done this before when you calculate effective stresses in soils. When you calculate effective stresses, you subtract out the pore water pressure, because that's what that is that hydrostatic stress. You don't really care about the total stress. You care about the effective stress. So you take out that water pressure, and you probably know what I'm talking about. It's the same idea. So what we do is we calculate what's called a deviatoric or deviator stress tensor. And all it is we take our original stress tensor and we subtract out the average normal stress. Okay? So we subtract out the sigma average. And how do we calculate sigma average? It's just that. Which, keep in mind, sigma x plus sigma y plus sigma z, that's I1. Make sense? So by that very token, we can calculate, if we had an I1, an I2, and an I3, we can calculate a J1, a J2, and a J3. Now, if you think about it, that I1, it was the sum of the terms along the main diagonal. What would the sum of the terms along this main diagonal be? Think about it. What would, if I took this plus this plus this, I would have sigma x plus sigma y plus sigma z minus 3 sigma averages. So minus 3 of these. So what would the sum along the main diagonal be? 0. It'd be 0. So what is J1? J1 0. Okay, it's always 0 by default. Now, likewise, we have J2 and J3, and it's the same process. Okay, the same process. We can do a little bit of algebra and some substitution to come up with some really simple values for J2 and J3, as you see here. Now, my steel design folks, they will know this term, or they better know this term. They better. Like it or not, or whether they believe it or not, they have already done problems incorporating J2 plasticity. They already have, because there is another name for J2 plasticity, and we call it the von Mises criterion. If you expand this out and actually expand it in terms of just your original sigma x, sigma y, and sigma z, and you actually look up the von Mises yield criterion, there it is. So J2 plasticity is also called the von Mises yield criterion. So you've all done this before, I promise. Okay. Last note, this is just food for thought, and this is probably a little bit geared more towards the mechanical students in here. If you've got stresses, along some, some three-dimensional stress state, and you want to determine what's the other or three-dimensional stress state along some given rotation, it's just a function of applying your unit normal vector. So if you want the stress along some plane, it's just your stress tensor multiplied by your normal vector. And along this stress plane, you can get a normal stress component and a shear stress component. How do you get the normal stress component? Take that and dot product. All right. How do you get the shear stress component? It's just sort of a blown up Pythagorean theorem. And that's really all there is to it. All right. Make sense? Okay, so what I want to do is do this problem with you all together. Okay? But when I say do it together, I really want you all to kind of do it on your own. Okay? So I want to see what you get. So I want you all to open up Excel, and we'll start it off with the principal stresses. So I want you all to open up Excel, type out this matrix, and I want you to tell me what the eigenvalues of that matrix are. So given a stress state, I want you to tell me what are the principal stresses, which this stuff has direct application. This type of stress tensor would be most likely generated by a plane strain analysis. So if you were analyzing something like a dam or a retaining wall, it would be calculating stresses based off something that looks like this. Okay? So I want you all to tell me what the principal stresses are. Now you can do it with Matlab, you can do it with Excel. I'm actually going to leave it open-ended. What's that? Oh. Now there are 3 of them. So if you use Excel and you have to use goal-seek, make sure that your initial values are, like, you either want to guess a really, really big value or a really, really small value. You might have to play around with it a little bit if you use Excel. It's just one of the I guess you could say, disadvantages of doing it using Excel. Excel probably is a little bit easier. Either way you want, it doesn't matter. Okay, so you got one of them. That's one of them. Okay, one thing if you're doing that, your rows will be separated with commas. And then when you get to your next row, that's when you use a semicolon. Okay, you got one of them right there. That's good. I'm going to set it up both ways. Clear all, and then we'll say A equals, and then let's see. Nice. All right, let's see. I got all my signs right. I did. No. You just EIG, and then A. That's it. There you go. Okay. I'll also set it up in Excel as well. So our original matrix, 20. All right, for those of you doing this in Excel, I'll turn the screen back on and show you what I'm working on. You can do it in Matlab or Excel. Either one's fine. Let's see. This turn on. All right, so what I've got here is here on the top, this sort of shaded matrix up top, that's the original one. And then I know there's going to be 3 eigenvalues. So I said, all right, let's put one here, one here, one here. And these are just some random numbers I filled in. Based on these random numbers, I've got my lambda i's right there. So if I wanted, I could change this first one to, like 74. Then there it goes. Okay? Then this matrix here is my original matrix minus that, and then here's my determinants here on the side. So I'll go ahead and help you out with the first one if you haven't already gotten it. So like I said, what's the easiest thing to do is to pick a really, really big value. We'll say like 100. Then we'll do our goal seek. So we want to set that value at the very end to be 0 by changing that 100. Do the goal seek, and we get an even value of 50. So 50 is one of your principal stretches. Well, it comes out to like 50.00001, but numerically it's actually equal to 50. So that's your first one. There's 2 more, and I will let you all find them. Let's see. Okay, you did the Matlab version. Yep. You don't need to set it up 3 separate times if you don't want. Yeah, well, that's fine. Just make sure that your references are right. And again, you need to take the determinant. It is snowing, but it is certainly not sticking. It's just sort of flurrying. Yes. Where's your determinant? Oh, okay. You have to calculate the determinant. All right. Do you know how? Okay. You say equals m, the term of all that. And there you go. So what you should find is, watch this. If I change this value to say 11, it'll change that, and you want that to be 0. So you go down into what if. I am showing you the Excel version, and you probably do want to get at least a little bit marginally comfortable with it, unless you're a little more versed in Matlab. The reason why is because later on we're going to do dynamic analyses or buckling analyses. Let me ask a question. You all are in advanced vibrations, right? Are you using finite elements in there at all? But you all know what I mean by when I say like natural frequency and all that. I would hope so. That whole class is about natural frequencies. What we'll do in here is we'll take a finite element approach to a given problem and use finite elements to determine natural frequencies and what have you. And it's all about determining eigenvalues. So, what's up? I set this value to equal 0 by changing that. The eigenvalue, the guessed eigenvalue. So this is my lambda right here. That's lambda. These are my lambda times I matrices. This is A minus lambda times I. And these are determinants. I want to set the determinants equal to 0 by changing the lambdas. Okay, so you got the 50. Well, that's close enough, but now you've got to pick a different seed. Okay, you've got one. What'd you get? 20? No, well, these aren't. I haven't done these. I said the first one's 50. Like this one's different. Like if I've only goal seeked the first one. Let me go ahead and goal seek the rest. Okay, that one's 20. And then your last one, they go in order. Like I would start off with like a really small value, maybe like negative 100. And there you go. Those are your answers, 50, 20, and minus 50. Yes? Well, you got it right because you want it to be 0. You want it to be 0. See, watch this. If I change this to like 24, oh, that's why. You're not referencing this. That's the whole thing. If you don't reference it, it's not going to work. So So let me equals that equals that. See, what you want is, okay, if I change this eigenvalue to like 26, you want it to affect everything else. Now, for those of you that did this in Matlab, this took about 2 seconds. Yeah, because all you do in Matlab is this. Like you literally just type in your matrix, like define it, and then just eigenvalue of A, which is nice. But one thing I will say is when we get to matrix analysis with vibration and buckling, it'll be a little trickier. So, little trickier. All right. Let me make sure everybody's good. What's that? Okay, it's your determinant, right? Hold on, let me see something. What are you calculating the determinant of? No. You calculate the determinant of this. Remember, it's a determinant of that. See, what you want is, if I take this value and make it 6, I want it to change that. Okay, so if I go what if goal seek set that equal to 0 by changing that. Does that make sense? What's up? Okay, that's one of the things where your initial seed value, does kind of affect it. Like, let me put it like this.
Oh, what you're trying to.
What you start it from, yes. So like if I put minus 50 over here, like that'll give me there, and if I put 50 here, that'll work. But see, the problem is, okay. Well, see, watch this. Here, I'll show you. Because let me pull something up because I want this on the recording as well. Okay. One of the things that you have to make sure that you're keeping in mind is your initial guess. Like, for instance, the answers are 50, 20, and minus 50. Okay? Now, your initial guess is going to affect what your eigenvalue is. So, for instance, if I don't know right here, and I make my initial guess 51, and I tell it to iterate, so if I go what if goal seek set that equal to 0 by changing that, it gets to 50 and it stops, yeah. So it's stopping on the first one. Like, you can't put in a seed value of 51 and expect it to spit out 20. You see what I mean? You're not going to get there, okay? Excel's going to say, well, gosh, 50 is what you're after, and it's going to stop, okay? So I will admit, that is kind of a disadvantage of using Excel, is that with its iterative process, it's going to stop when it finds an answer. So there is a point where you kind of have to have a little bit of a crystal ball. That's why, like, if you've got 3 eigenvalues, I say that what you should do is start off with a value that's very, very big, start off with a value that's very, very small. That'll at least get you 2 of them. You know the other one's somewhere in between. That's what I'm saying. And if you want to do like 10,000 or negative 10,000, start off really, really big. Yeah, there you go. Yeah, start off really, really big and then get small. No, it's all about your starting values. Yep. Okay. Yeah, exactly. You're gonna keep getting the same too. Now you can always check your work using Matlab. I mean, it'll just spit it right out to you. All right. I know that a lot of people, you either love Matlab or you really hate it, and I get that. But this is an application that's really simple. It's not complicated at all. You literally just type in your matrix, EIG, and that's it. Right there. That's all there is to it. Does anybody have any questions? Okay. I want you to be comfortable with this concept of eigenvalues because we really have 2 final types of analyses that I want to teach you all before we open up FEMAP. And that is, how do you compute the natural frequency of a structure? What I mean by that is this, okay? So, because I've got to do a little bit of dynamics with you. So, if I look at this appurtenance on this podium here, This can be treated as a cantilevered beam, okay? Now, if I take my hand and I hit it, it vibrates, okay? It vibrates, okay? One of the fundamental laws of just physics and structural engineering in general is that under free vibration, everything vibrates according to its natural frequency. It's one of the reasons why a guitar works the way it does. For instance, how many of you have ever played a guitar? Okay? If you take the G string or an E string or a B string on a guitar and you play it really, really lightly, or you play it really, you wail on it, don't get me wrong, the sound may sound a little rougher, but it's the same note. It's the same tone. It's because that string has the same mass, it's the same length, it has the same stiffness, and when it's vibrating freely under its own free will, it will vibrate at the same frequency every time, okay? That's what a natural frequency is. It's one of the reasons why a guitar works. It matters to mechanical engineers because how many things do you all design that involve some type of dynamic forces? How many engines or aircraft or missiles or how many widgets have things moving? Vibrating forces is something you all deal with on a regular basis. It matters to civil engineers really for one very specific application, a very big one, but a very specific application, and that is earthquakes. Okay? So it does matter. Okay? The second type of analysis that I want to teach you all is a buckling analysis. In other words, things in compression will just tend to stretch, but you can't take, if you have a slender element, you cannot take the same force and tension and expect it to behave exactly the same in compression because things in compression like to buckle. Okay? So what we want to do is determine how to calculate buckling loads, which are essentially eigenvalues as well. So we're going to learn about some new matrices. Like you all know about stiffness matrices, we're going to talk about mass matrices. So for vibration and for buckling, we know about regular stiffness. We're going to learn about geometric stiffness. But in the end, it all goes back to a buckling load. And furthermore, it goes back to eigenvalues. That's all I have for you all today. Let me go ahead and stop the recording. I didn't get the sign-in sheet passed around, so let me do that. Let me stop that. And I will see you all next week.